y'all, I'm Molly and I study acoustics. In this video, we're going to discover a little bit about acoustics and some music making through a ruler and a little bit of help of math. Yeah, you heard me right. This ruler can play music.
Musical rulers with Molly.
You see, music notes are created by changes in vibration. So the faster something vibrates, the higher the pitch is produced, and the slower something vibrates, the lower the pitch is going to be produced. A simple way to change the speed of vibration is changing our length of the object that's moving. So here I have a ruler, or I went to a painter store and got some painter sticks. You can use even a flat wooden spoon, whatever you got around the house. I'm going to hold my ruler one end against a flat surface like a table, and I'm going to leave the other end loose so it'll be able to vibrate up and down. If I pluck this loose end, we can see this ruler is vibrating kind of like a diving board. If I move the ruler to overlap this table more, so now I only have a little bit hanging off the table, less length is able to vibrate. So if I pluck it, now we get a much quicker vibration that goes up and down, to the point where you might not even be able to see it. So here we have our low and slow vibration. And then when we bring it up, we have a quicker vibration. But if you want to customize your ruler to make a song of your own, take out your listening ears and mark where you think the length matches that right now. I'm using this painter stick so I can write on it, but if you want to use your ruler for this, put on some masking tape so you can write over it. I'm going to do Here Comes the Sun because I'm a big fan of the Beatles. I'm going to pick my highest note first because that's probably going to be the hardest to play. If I play it up here, can't really hear it. Yeah, that one sounds good. Notice that this side, how fixed it is going to change the pitch, so try to keep this hand around the same every time. There we go. I'll mark that as Here Comes the Sun, here. So now I gotta find comes. Here we go. So we got Here Comes the Sun. There we go. Let's do it together. Here comes the sun. Woo! Now, cantilever beam vibrations are a little difficult, so that's when it vibrates like a diving board. But when we look at strings, those are a much simpler vibration pattern that actually works really well with some mathematics. So now go grab a string, whatever you got at home, and let's work a little bit with that. So I found a rubber band lying around the house, and I'm going to utilize my ruler again to hold it stretched in place by kind of wrapping it around both ends, so make sure that it reaches both sides of your ruler and that your ruler can lay flat. So now you have this. Then I'm going to place two markers on each end so that we can have our rubber band up a bit so we're able to pluck it. Now if I want to change the length, I can move one of these markers. Again, we have decrease in length increases our pitch. Another cool thing that happens with our strings, since they're fixed on both ends, is that every time we half the length, we can double the pitch, which in Western music, we observe it as an octave. So I'm going to start this one near the end as far as possible. And then I'm going to move my other marker to the 20 centimeter mark. So you see right there. And let's pluck that. Okay, now what would be half of 20 centimeter? 10 centimeters. So I'll move this all the way up to my 10 centimeter mark and pluck that again. We got an octave. Now let's do that one more time. So half of 10 would be 5. So we've got our root and an octave and another octave. Now you're officially a musician, acoustician, and mathematician. Have fun with your new musical instrument, and thanks for watching.
Musical rulers with Molly.
Hi everyone, my name is Martin Lawless and I am a visiting professor of mechanical engineering at the Cooper Union. Today we're going to learn how to make an ocarina from our hands. We need to start by forming a cavity with our hands, and we're going to do that by putting our hands together. First, take both of your hands and put them like so with all your fingers together, as if you were going to be putting on a mitten. Your fingers should be closely spaced together so that they form a nice seal, and I could test that by trying to blow air through, and I shouldn't feel any air pass through. Once I have that, I'm going to take the pinky's edge of my left hand and place it in the seam of my right hand between my fingers and my palm. Again, this is to form a nice seal, so it's going to look something like this. Once you have that ready, you can curl your fingers of your left hand so that your fingers touch your thumb, like so. For convenience, I could also curl my fingers of my right hand over just to make it a little bit more comfortable. So I now have it look something like this. And finally, I can bring my thumbs together so that the knuckles are almost touching one another. And you can see that I have a nice hole there between my knuckles. So now we need to test whether my cavity is properly sealed. And we can do that by blowing air into the cavity. So with that hole that we just created, I'm going to test it by blowing directly into the hole. And what you should feel is your hands trying to expand outwards as the air presses in. I could also test it by drawing in a breath. And then you should feel your hands being sucked into the cavity. If you have a hole in your cavity, so I could put a hole here, if you have a hole and blow, you're going to both feel and hear the air in the cavity. And that's a problem. We need a nice seal. So if you hear or feel a hole in your cavity, what you should do is go back to the previous steps, try again to put your ocarina together. So now that we have the ocarina together, let's learn how to play it. I don't want to blow the air directly into the cavity because we did that before and we didn't hear anything. Right? So instead, what I want to do is actually blow the air downwards. And there's a little bit of a trick in order to do that, where we're going to treat our thumbs sort of like a whistle. So again, we have our cavity together with our thumbs pressed together so that our knuckles are close. And I'm going to place my upper lip above my knuckles and my lower lip below my knuckles. When I do that and I blow air, the air should travel downwards. Let's practice a little with our hands open. With our hands open, we could put the knuckles together, all right? And I'm going to slightly bend them a little bit so that I have a nice platform for my lips to rest. With the knuckles bent, I'm going to put my lips over my knuckles and blow. As I blow, I should feel the air travel downwards so that it hits my palm and my wrist. When I do that, what's going to happen is that some of the air is going to travel into my cavity and some of the air is going to travel out of my cavity. And that's going to allow vibration to occur so that we hear a sound. So now we could try with our ocarina. I'm going to put our ocarina together, as we showed before. I'm going to put my lips over my knuckles and blow downwards across the hole. Let's talk a little bit about how the ocarina works. When my hands form a cavity, the air inside the cavity acts like a spring. We felt that the air pushed back against us when we blew into the cavity. That's the spring at work. The air in the hole between our thumbs then acts like a mass. When I blow across the cavity, the mass is pushed into the cavity, while the spring pushes it back outwards. This occurs over and over again as I blow across the hole, which causes the mass to vibrate at a certain frequency, which we hear as sound. Now, I have a question for you. If I were to make my cavity smaller, the spring gets stronger because it is now harder for me to add air to my cavity. There's less room. What do you think happens to the frequency of the sound that we hear? Does it go up or does it go down? Let's do an experiment with our ocarinas to test this question out. So first I'm going to put the ocarina together like we showed before, and I'm going to play a note. I'm then going to make the cavity of my hands smaller by bringing my hands closer together and playing again. The note sounds higher, which means that the frequency of our sound increased. So, when the spring of our cavity is stronger, that means that our frequency increases. We could play around with our cavity size and maybe even add some holes to play a song. Yeah, like so. So now that you have an ocarina at your disposal, I hope you enjoyed this video, and go out and enjoy your ocarinas.
Hi, my name is Dan Russell. I'm a professor of acoustics in the graduate program in acoustics at Penn State, and I'm going to show you how to play music with a bottle. Now this looks like an ordinary bottle, but to an acoustician this is a Helmholtz resonator. Helmholtz was a German scientist in the 1800s who studied a lot of acoustics and vibration devices, and we call it a resonator simply because it's an object that oscillates. In order for something to oscillate, you have to have a stiffness or a spring part of the system, and you have to have some kind of a mass or some kind of a heavy object that causes inertia. And if I hook the mass and the spring together and pull them down and let them go, it will oscillate. The spring tries to pull the mass back to its normal position, and the mass, once it's moving, wants to keep moving, and it goes too far. That's what oscillates. Well, a bottle is just like a mass spring system for an acoustics person, except that if I hold it upside down, I can say that the spring part of the bottle is the air inside the cavity of the bottle, and the mass is the air in the neck that moves all as one piece. And when I blow into the top of the pop bottle, you can make the pop bottle sing at the frequency just like the mass spring system moves back and forth. Well, if I wanted to change the frequency of a mass spring system, one way I could do that would be to change its stiffness. So if I use a shorter or a stiffer spring, when I pull it down, it will oscillate faster. Well, with a bottle, the easiest way to change the stiffness in the volume is to add some water to it. Fill up the volume with water so there's less air, which means there's less spring, smaller area for the smaller volume for the air to squeeze, which means it's a stiffer spring. So now I've got a different frequency. And if I take a bunch of these, a bunch of bottles, with the right combinations, the right heights of water, I can form a musical scale. I get them all together here. 8 bottles, different amounts of liquid in each bottle. Now if I put them all together, swap those two in the right order. If I have a scale, I can play music. Merry Christmas! When you blow in a bottle, the bottle with the most liquid, the smallest amount of air, has the stiffest spring, and so it has the highest frequency. And a bottle with less water or more air has a softer spring, so it has a lower frequency. But if you tap the bottles with a stick instead, the bottle with the most water has the lowest frequency. Because now the water is acting like a mass, and the more mass something has, the lower its frequency. The stiffness in this case comes from the vibration of the bottle. The glass is not the air moving inside the bottle. It's the bottle of the glass is actually vibrating. So the glass provides the stiffness, and the amount of water in the glass provides the mass. So now I can adjust the amounts of water, I'm adjusting the amount of mass, and I'm changing the frequency. And I can change the notes just right to make a musical scale also. So again, I can play music. Merry Christmas!
I'm going to do a quick demonstration about how parts of the speech system work. So I want to start with our voice box or our vocal folds. So if you take your fingers, put them right here next to your Adam's apple on the side. And if you make the sound zzz, you should feel the nice vibration. That's your vocal folds vibrating. Zzz. But if you make the sound s, right, you won't feel that same vibration. This is one of the ways in which we make differences between sounds, as we make the zzz and the s, and make those sounds sound a little bit different based on that vibration in our vocal folds. So what we're going to do is we're going to make a model today of speech, and by starting out with our duck call. Makes a sounds like this, and that's all we need for that. Now what we're going to do is we're going to talk about the rest of our speech system. Okay, so everything above the vocal folds, and what I want to do is I want to show you a quick picture of kind of how my speech anatomy might look. Right on the left-hand side here, you can see my nose, you can see my lips and my teeth, and this is just kind of showing you the inside of my speech anatomy. You can see my tongue here, and each of these things is going to do something as I speak. Now what we're going to do is we're going to think of this open area between my tongue and the roof of my mouth kind of as a tube. So in order to do this, we're just going to draw some lines on our drawing here. We've got this circle here in the front that represents the opening at our lips. And then down here we have a dark gray circle with a little opening. This is our vocal folds. Okay, and in between we've just drawn a couple lines to make a tube. Now if we pull that tube out of our vocal tract, we get something that looks like this L-shaped tube, and I'll show you with this plastic tube that I have sitting here, right? So we have a little bit of an L-shaped tube. And what we're going to do with our L-shaped tube, or upside down L-shaped tube, is we're going to flatten it out. And when we flatten it out, we get something that might look like this. So on the right-hand side, we have that dark circle again. That's where our vocal folds are. And on the left-hand side, we have that open circle. This is where our lips are going to be, and the end of our tube. What we can do is if we take the duck call as our vocal folds, and we take a small tube and we put the two of them together, we can actually do a demonstration of some speech. Now what I want to do is I want to talk to you a little bit about how we make speech before we look at this. So we're going to do the vowels E and Ah. Now with E, if you say E, my jaw is nice and high, and my tongue, it comes up towards the roof of my mouth. And then if I do Ah, my jaw lowers, my tongue comes down, my tongue kind of slides back. What happens is we create a big tube in the front for the ah and a little tube in the back for that ah. But for the E, we create a little tube in the front and a big tube in the back. Okay, so we have two different tubes. So now when we take our duck call and our tube and we put the two of them together, we've got kind of our vocal tract, and now what's missing is the big articulator, and that's going to be our tongue. What I've done is I've borrowed some Play-Doh from my daughter along with a skewer. I'm just going to stick the Play-Doh in here into my tube, and now we can move the Play-Doh back and forth within our tube. So now when the Play-Doh's in the front, I have something like an E vowel, right? Small tube in the front, big tube in the back here. And if I move my tongue back, I've got a big tube in the front and a small tube in the back. This is a demonstration that Johann Sundberg has done a few times. So now I'm just going to show you how this might work. So we have ah. So that gives us a nice kind of ah-e distinction. And this is nice because you can kind of see how the tongue might move in that space. I'm going to give you another way of doing this. And what I've done is I've taken the equivalent of what I would call a pool noodle, if you have one of those laying around, and I've just cut a little piece of it off and I'm putting it on my duck call. And what I'm going to do is I'm going to blow on this, and now this time, because this is soft, I can squeeze it. So I'm going to squeeze in the back to get an ah, and I'm going to squeeze in the front to get my e. And if I'm fancy, I might try to do something more like a consonant in the front. So if I keep it squeezed in the back for an ah, I'm just going to squeeze in the front real quick here to try and make it sound like an ah-pa. And this is just a quick kind of fun demo that you can do to demonstrate kind of how the basics of speech work.
Hi, my name is Andy Piacsek. I'm a physics professor at Central Washington University. And I want to show you how you can demonstrate a very powerful idea in physics and music using just your mouth and a portable sound source like an electric razor. So here's the powerful idea. Most sounds, like those from musical instruments and our voices, are actually composed of many simple or pure tones, each tone having a particular frequency and loudness. The quality of the sound, what makes a violin sound different from a flute, for example, depends on how loud each component tone is. This is really the same idea that light from the sun is made up of individual colors of the rainbow added together, and each color has its own wavelength. We can easily test this idea for light using a prism. But do we have something like a prism for sound? Can we take a complicated sound and somehow find out what the component tones are? This is where your mouth comes in. But to understand how that's going to work, let us compare our mouth to an empty bottle. Both are essentially cavities with a relatively narrow opening, and this shape causes sound to resonate at a particular frequency. You can hear this effect when you blow across a bottle and get a tone. And this also happens when you whistle, since your mouth is acting just like a bottle. Now, if you've done either of those things, you've probably noticed that the pitch depends on the size and shape of the bottle, and also your mouth. Those sounds are very close to a pure tone. Well, let's compare that with the sound of a violin. So even though those two sounds had nearly the same pitch, I'm claiming that the richer sound, the sound of the violin, consists of more than one tone. And the reason we don't hear multiple tones competing for your attention, like the sound of a gong, for example, is that the components of the violin sound have frequencies that are simple multiples, called harmonics, of the lowest frequency component, which we call the fundamental. In this case, we hear only the pitch of the fundamental. For example, if a sound is made up of a 100 Hz tone and a 200 Hz tone and a 300 Hz tone and so on, then you will hear only the pitch of the 100 Hz. But the quality of the sound will depend on how loud those other components are. I can demonstrate this using the recorded sound of a trumpet. Next, I will play the fundamental and the next 11 harmonics of that sound played individually, one after another. These frequencies get pretty high. Now, listen to those same 12 tones, but this time I'm going to layer them on top of one another, starting with the fundamental. Did you hear how the sound evolved from a pure tone at the fundamental to something similar to a trumpet sound as each harmonic was added. Okay, I needed a computer to make that audio demonstration, but I'm going to show you how you can use your mouth to demonstrate that sounds have components. Now this works because your mouth is a resonator, which means it will amplify whatever frequency you've tuned it to based on its shape. So if a sound has a component with that particular frequency, it will get louder in your mouth. And since we can change the shape of our mouth, we can tune it so that different components of the sound are amplified. Let's give it a try. I like using an electric razor for this demonstration because the sound is steady. It's not constantly changing like music or talking. And if you listen closely, it actually has a pitch. You can hum along to it, which suggests that some of the components are harmonics. Ooh. Okay, so I'm going to do this. I'm not going to hum along this time. I'm just going to hold it up close to my mouth, and I will change the shape of my mouth, and let's see if we can hear the different harmonics. There you go. Sounded maybe tried to play taps there with my mouth, but which is only 4 notes. See if you can give it a try yourself.
Okay, this is a demo that I really like to share with people when I have the chance. And this is a music box that I have. And if I play, or if I crank on this, it plays a little tune. Which I think, you know, you can hear and recognize that tune. I have the music box has a little mechanism inside it, and there's this, you know, this very simple box that's around it. And I have a different music box mechanism here, and there's no box around it, and there's nothing on the back. It's just the metal. And if I play it, you should predict what you think you might hear. I'll let you know it's a different tune, but listen very carefully. You hear that? You hear the difference? A lot softer, right? So why is that? Well, the only thing that's mostly the only thing that's vibrating in this case are the tiny little tines of the music box mechanism that you can see, you know, right there, and they're really, really small. But if I hold this thing up to just pretty much anything that's big and flat, like I have a clipboard here. If I hold this onto the clipboard, I actually haven't tried this, so if this doesn't work, you may boo. Hear that? It's a little louder. I had some really good luck using this as a shelf off of a cabinet that I took apart earlier this week. I think that's significantly louder. All right, and then just to show, like, it really doesn't matter what you use. This is a piece of cardboard that, you know, came in the mail today. And again, to compare it to this without it, the amplitude difference is striking, right? So why does holding it up against anything really make it louder? This is an example of sympathetic vibration. So, you know, this piece of cardboard and the clipboard and the piece of shelf, none of these have resonance frequencies that are anything, you know, related to the notes playing in here. But all of these had surface areas that were much, much greater than the surface area of the tines in the music box mechanism. So if you think about when this is cranking and this is the only thing that is vibrating, the tines are the only thing that are moving, and therefore moving the air molecules that are radiating the sound. Whereas if I place this up against here, the tines vibrate, and then those vibrations are transmitted through the body of this mechanism into whatever surface it's on. And the surface area of this shelf is huge compared to the surface area of this. So there's a lot more of the air molecules that can be vibrated, cause to vibrate, which cause overall a louder sound. So I really like it. This is the sort of thing that stringed instruments depend on. The waves from the string are transmitted via the bridge into the soundboard and then out to the audience. So that's my demo.
There are several ways to make craft stick harmonicas. The way I'm going to show you first is using 3 rubber bands, 2 craft sticks, and 2 straws that serve as spacers between those 2 craft sticks. First, you take your biggest rubber band and put it lengthwise over one of the craft sticks. Then you can slip the pieces of straw, they can be about an inch or so long, underneath that rubber band, one on each end. Then you put your other craft stick on top, and then you just have to keep it pushed together or seal it together with the other 2 rubber bands, putting it around the ends like thus. Your finished craft stick should have the rubber band on one side and then nothing on the other side and held together. If you don't have enough rubber bands or long enough rubber bands, you could also use a strip of paper. And so here I'm just showing a different way of making it using a piece of paper, construction paper, instead of the rubber band for the lengthwise. Once you've created your craft stick harmonica, you can use it to produce sound. But how do these work? Let's take a closer look. I went into my lab and took some pictures with my Photron Nova high-speed camera to see what's happening in the sound stick. When you blow on your craft stick harmonica, you cause the rubber band to vibrate. How fast it vibrates depends on how hard you blow and how tight and heavy the rubber band is. Before I play the video from the high-speed camera, I first want to orient you to what you are seeing. You can see the top line that I'm highlighting in blue and the bottom line. Those represent the top and bottom craft sticks. We also have the straws that you can see in green on the edges. I will now play the video. Here it is in slow motion. Between the 2 craft sticks, you can see the rubber band moving up and down, with the middle, where you're blowing, moving the most. It starts out moving all together in an arc, but then it runs into the top stick. As it does that, the movement becomes disorganized, and other shapes begin to form in the band as it moves up and down. This causes multiple pitches or frequencies to be produced at the same time. You can change the overall pitch produced by your craft stick harmonica by changing the length between the 2 straw pieces. For example, with my craft stick, if the straws are about 7 centimeters apart, I get this sound. However, if I move the straws closer together, this is the pitch I now produce. You can tell the pitch is higher when the straw pieces are closer together. You can also change the pitch produced by your craft stick harmonica by changing the thickness or tightness of the rubber band, or you can change the material, like I did when I changed to paper. Here's what the paper looks like in slow motion. Here is a magnified view of the 2 craft sticks with the paper in between. The paper is wider so you can see it bends side to side as you blow in the harmonica. It also vibrates faster with many different shapes, which creates an overall higher pitch compared to the rubber band. Here is a direct comparison between the rubber band and the paper with the straws the same distance apart. Here is the rubber band. And here's the sound produced by the paper. You can tell, even though the straws are the exact same distance apart, the pitch produced by the paper is much higher than the pitch produced by the rubber band. Now that you know a little bit about the acoustics of craft stick harmonicas, I encourage you to experiment with your own harmonica to see what sounds you can produce. You can modify your harmonica by changing the rubber band, changing the length between the straws, or changing the material. If you can produce enough sounds, you can eventually start to play a song.
Good morning, my name is Fernando. Today I want to talk to you about sound and of a very important aspect of sound, which is the speed of sound, which is the speed at which sound propagates in different media, such as air, water, or even steel. You may have experienced the following. When you're outdoors and you see a lightning strike, you first see the light of the lightning, and sometime after you can hear the sound of the thunder. This is because the light of the lightning propagates at the speed of light, which is 300 million meters per second. But the sound of the thunder of the lightning propagates at a speed of 343 meters per second in air, much slower. The speed of sound in a medium such as air, water, steel, or even concrete depends upon two quantities. It depends upon the stiffness of the medium, how much the medium resists being deformed, and the density of the medium, which is the amount of mass the medium has per unit volume. So I will use this, a slinky, to prove the relationship between the speed of sound and the stiffness of the medium. So ready? Let's go check it out. So I have stretched out the slinky, and you can see that a pulse can propagate through the slinky in the same way that sound propagates in air. You can see that when the slinky is stretched out, the pulse propagates faster. And when the slinky has a shorter length, the pulse propagates slower. When the slinky is stretched out, its stiffness is high because you need more force to deform it. And in accordance to the law that we saw on the blackboard, when you have more stiffness, the speed of sound is higher. And you can see that when the slinky is stretched out, the speed of the pulse is higher. When the slinky is shorter, its stiffness is less, and the pulse propagates at a slower speed. It can be proved that the time it takes for a pulse to propagate from one end of the slinky to another is independent of its length. Why is this? When the slinky is longer, the speed of the pulse is high. But it needs to travel a longer distance. When the slinky is short, the speed of the pulse is slow. But it has to travel a shorter distance. So, I hope you have enjoyed this short demonstration of the speed of sound. So, always remember, the stiffer the medium, the faster the speed of sound in that medium. The denser the medium, the heavier the medium, the lower the speed of sound in that medium. So, greetings from Argentina. Have a good one.
Hi everyone, we are the Monsons. I'm Brian Monson. I'm a professor at University of Illinois at Urbana-Champaign. And what's your name? What's your name?
Johnny.
And you are?
Levi.
And who are you?
Kai.
And how old are you, Kai?
3.
How about you, Levi?
5.
How old are you, Johnny?
5.
Okay.
And I'm his twin.
That's right. And today we're going to teach you how to make a voice box, what I call a voice box. What you're going to need is a regular old Kleenex box. You can use any kind of Kleenex box you want. You can see these, we've already cleared these out. They're empty Kleenex boxes. The plastic film is gone, okay? You're also going to need rubber bands. Here we go. These are rubber bands. I'm going to put those right there. And crayons or some other sort of writing utensil. You'll see what those are for in just a moment. And you probably want some tape, okay? Okay, do you guys know what your voice box is?
Something that you use like a guitar.
Yeah, that's what we're gonna make. But what's your real voice box? Look at this. Do this. Put your fingers up on your neck and go like this. Ah. Do you feel your fingers vibrating?
Yeah.
You feel your neck vibrating? That is what we call your voice box. Do you know what's inside your voice box?
What?
It's called vocal cords. Your vocal cords, they're like vibrating back and forth. They're like on your voice box.
Like the smaller the boat, they're really rubber bands.
They look like this. Okay, everybody get a rubber band. Let me show you something cool. And hold it like this with your fingers, right?
Like this?
Yep, and what we're gonna do
It's like an arrow.
yeah, when you stretch it out, so do you know what happens when your voice goes up and down? Your vocal cords are going like this. They're getting kind of longer and shorter.
Like very fast.
Stretching and then getting back. Yeah, like this. So watch this.
But very fast like this.
Here's how it works. Watch this. Ah. Notice when I stretch it. Ah. Okay, so try that with me. When you stretch it out, your voice goes up, and when you bring it back, your voice goes down. Ready? Everybody go. Ah. So here's what we're going to do. We're going to make a voice box. What I want you to do is take your voice box, okay? First thing we're gonna do is take a crayon and you're going to tape it on the voice box like this, okay? On one side. Should we tape it? Here, can you hold that?
I bet lots more people are gonna try and make the voice box, right?
Probably. So we tape it down like so.
Can I let go?
Yep. Okay. So you're going to tape 2 crayons on the side like this. Can you see that okay? Or it could be a pencil if you have a long,
Can you get that?
Kleenex box. You can do that.
I was planning to use that green. Can you do it back, please?
All right, now what we're going to do, Kai, now you have your rubber band, right? We're going to put your rubber band on your box to make a voice box. Can you put the rubber band around your box? It goes around the top.
What are the crayons for? What are the crayons for?
Pull that down. There we go. Okay, now check this out. So the crayons, what they do is they hold the rubber band in place, okay, so that it makes a better sound. Let's check this out. Look what we're going to do. What happens if you pluck that? Can you pluck that, Kai? Do it. Hear that? Oh, that's making a note, right? Can you hear that note?
Yeah.
La, la, la. Can you sing that note? Yeah, nice job. All right. Okay, so everybody's got 2 rubber bands on your box now, right? Yeah, so you can change the note by pulling on the rubber band on either side to make it looser in the middle, and it goes down, la, la, la. Or if you pull it tighter to make it tighter in the middle, it goes la, 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 goes up, right? That's just what your vocal cords are doing. When you're going down, they're really loose and floppy vocal cords, like a loose rubber band, like this. Ready? And when you pull them tight, like this, your vocal cords are getting really, really tight, like your rubber band. Okay, so I made one before. I want you guys to listen to this. Here's something else to notice. When you have larger rubber bands, they make lower notes. And when you have smaller, skinnier rubber bands, they make higher notes.
I already know that, Daddy.
Cool. All right, check this out.
Can I?
Listen. I want you guys to listen. I think you'll recognize this. Are you ready? Listen carefully.
Twinkle, twinkle, little
You got it, yeah. So you can make a rubber band box like this.
And it's exactly like our vocal cords when we sing little, twinkle, twinkle, little star.
You got it, just like
It's
that, right?
It's just having we like these.
Yeah,
Except
when
we
we
don't
sing
have
low
different
notes.
sized vocal cords.
We don't. So for ours, our vocal cords, we just have 2,
Yeah.
and we're stretching them back and forth, kind of like when we were stretching the rubber band, right? Cool. Okay, so that's a voice box. Can everybody say goodbye and say have a good day?
Have a good day.